Hello. This video is the first of three that are going to be concerned with what we call exponential models. These are a fairly simple kind of model, and they depend on the exponential function. And this particular video will be introducing the models, talking a bit about the mathematics of the solution of problems that relate to them, and then we'll be getting into some examples of where we use exponential models. The second video is concerned with what are called the half-life models. These are common for radioactive decay problems and others types of situations. And the third video is concerned with financial models, and also I'll be looking at the classic problem of the Newton cooling law, which is also modeled by a decaying exponential function model. The exponential models do come up quite often in various situations as we apply models to issues that concern us, and so it's important for you to understand these. I will be assuming throughout these videos that you do have some sort of skill at using exponential functions, that you are in command of how you multiply exponentials, how you work with the log of a product, and so forth. So I won't be spending a lot of time explaining that, but you'll notice them as they go by in the numerous examples I'll be giving. The exponential models are described by a function which I've given here. P of t, we can think of it as a population as it is at time t, is equal to the initial size of the population, p of 0, multiplied by a factor e to the kt. And here t is the variable, time, and k is a constant, and it will control whether we're growing or decreasing and how quickly all these changes are happening. So k is a key parameter here, and so is p0, the initial value, this constant out in front. You can see that it's not much of a constraint to call that p0, because if you put t equal to 0 in here, we'll have e to the power 0, which is 1. And so we have p of 0 on both sides of the equality here, and we really do have an equation. So that p of 0 is the right thing to call the constant in front of e. Let's just start by taking the derivative of this function with respect to t. P of 0 is just a number, it's a constant, so we just write that down in the derivative. We then take the derivative of e to the kt. That's a chain rule. We substituted kt into the exponential. So we write down the exponential, e to the kt, and then multiply by the derivative of the exponent, which is just k. So we end up with this as the derivative, and what we see is that expression is really just k times what we started with. So this particular function is a solution of a differential equation which looks like this: y prime equals ky. So if I substitute p of t in for the y here, this will become a true statement about the function p, and we have a solution then of that differential equation. The phrase exponential model is applied to both the differential equation and to its solution. There are lots of examples of exponential models. For example, unconstrained growth. When a population is growing without any limits, it will grow following an exponential model. A radioactive decay follows an exponential decay process. Thermal transfer by convection is modeled by a decaying exponential model. That's what we mean by Newton cooling. Pressure in the atmosphere, for example. The amount of water which is held by a particular volume of air is an exponential model where the variable is the temperature of the air. And financial models. So there are lots of examples. Let's just now have a picture of what's going on. If p of t was 2, initial value 2, e to the 0.25 t, so that would be an example of an exponential model, we get a curve that looks like this black curve. It's an increasing curve. When t is 0, it goes through the point 2, and it increases quite rapidly. If, however, we have a negative exponent, so here I have p of t is 2 e to the minus 1/4 t, we get a decreasing curve. So whenever the exponent is negative, you will get a decreasing exponential, a decay process, and it decays quite quickly as well. So these are the pictures that go behind the models. Now, before we get into the examples, I want to just talk about the equation and the kinds of questions you can be asked about solving problems in this area. If we look at this particular function, it has 4 quantities in it: p of t, p of 0, k, and t. E is just a number, it's a fixed number. And so a particular question can be asking you to find any one of those 4 quantities given the other 3. So I've made a list here. For example, you could be asked to solve for k given t, p of 0, and p of t. That could be one of the kinds of questions you could be asked to solve. And because we are then saying look for one of these when we have the other 3, it's just a matter of knowing the right methods to use to algebraically isolate the one you're looking for. There actually are 5 types here in the list, and I've included number 2 here: solve for t given that you know k and the ratio p of t over p0. So if you're actually looking for t, you could deal with it just by knowing the ratio of p of t over p of 0, and I'll give an example of that as we go on through this video. If we actually are given k and t, we can calculate e to the kt with a calculator and get a number, and that just directly relates p of t and p of 0, so that's not a problem. If we're actually looking for k or t, they are in the exponent of the equation. Let me just bring that down. They're in the exponent of the equation, and so to get at them, we need to take logarithms. So we take the logarithm of that equation, and we get log p of t equals log p of 0 plus log of e to the kt. A log of a product becomes the sum of the logs. And then in these videos, log means log base e. Your course, our text may use ln, or natural logarithm, ln, for log base e. I'm just using log for log base e. So log of e to the kt is just kt. And so now, if we have p of t and p of 0, we can put those numbers in and directly solve for either k or t given the other one. So that's easy. And as I've mentioned, we could divide by p0, and if we know the ratio, then we can get at k and t by taking logarithms. Where this comes up is that it's not unusual in a practical situation to know this ratio. You don't necessarily know how many were there, but you may know that the population has doubled, in which case you can use that to get at both k and t.